Okay, to this video we're learning about pH and what you need to know about that. First off, what does pH stand for? It stands for the potential hydrogen. Now what does that mean exactly? Well, if we think about water, water we know is H2O. Well, something that we know about water is that it can dissociate into ions, and certain chemicals will cause this to happen, and certain chemicals will produce some of these ions. So for this potential hydrogen, the hydrogen we're thinking about, think back to what hydrogen is. It's one proton, no neutrons, with one electron orbiting. Well, the hydrogen we're talking about here is that sometimes this electron is given off to another compound, and hydrogen becomes an ion, and it basically just becomes one proton, which you guys know is positive, and we have this, sometimes this is just referred to as an H+. That's what potential hydrogen means, is the potential to produce these. So let's keep that in mind as we take a look at what is meant by pH and what I need you to know. Okay, here's some basics about the pH scale. The pH scale, we'll kind of draw it out here, goes from 0 all the way to 14. Right in the middle, 7. 7 is completely neutral. Bottled water has a pH of 7. Now, as you go towards 0, you become more and more acidic. And if you go the other way, between 7 and 14, you become more and more basic. So we can go 6, 5, 4, 3, 2, 1, 0. We can go 7, 8, 9, 10, 11, 12, 13, 14. So this is our pH scale. As we become more and more acidic, what that means is there are more and more of these H+ ions in that solution or in that cell. As we become more and more basic, it means we have the other side of the water molecule. So if you were to take a look at an H2O and take an H+ away from it, you'd be left with an OH, but you'd have that extra electron. It'd be an OH negative. We call this a hydroxide ion. So acidic, you have more and more and more of these H pluses. The more basic a solution is, you have more and more and more of these OH minuses. So what does this actually mean? Well, if we take a look at this, let's say orange juice is probably around a pH of, let's say, 5. Okay, and you can drink orange juice and it's not going to cause you any problems. But if we go down here to a pH of, let's say, 2, that is what your stomach acid is. Stomach acid is an acid called hydrochloric acid, and it can do damage. People that have acid reflux, or even someone who suffers from bulimia, that acid coming up the esophagus, getting into their mouth all the time, it can cause a lot of damage. And the reason why is because there's so many of these H pluses in it. So why can you drink orange juice and be okay, but stomach acid can cause problems if it gets where it's not supposed to be? Let's take a look here. We're going from a pH of 5 to a pH of 2. So each step in the pH scale represents a 10-fold concentration difference in these H pluses or in these OH minuses, depending on which way you're going. So to go from 5 to 4, there are 10 times more H plus ions. To go from 4 to 3, it's another 10 times. And to go from 3 to 2, it's another 10 times. So to go from a pH to 5 to a pH to 2, it's 10 times 10 times 10 equals, it has 1,000 times more of these H plus ions than does the pH of 5. So what does that mean? Well, you all realize from our study of chemistry that these H pluses, they're going to want to grab electrons from something else, or they're going to want to combine with other compounds because they're so positively charged, and because there's so many more of them at a pH of 2, there should be a 2 right there. There's that many more of them to do chemical reactions, and chemical reactions that are going to cause damage to the cell or cause a cell to die. So that's why strong acids are so dangerous to cells and to living things. Strong bases, it's the same thing, but it goes the other way. Let's say baking soda, you guys tested it in the lab the one day. It has a pH probably right around 8 or 9. Let's just say it's an 8. Bleach has a pH of probably around 12. Baking soda, we use it to bake cookies and things like that. You could mix up baking soda and drink it. It's not going to hurt you. But a bleach at a pH of 12, I mean, it bleaches clothing. It could damage your skin. It's a pretty nasty chemical. And if we do this math again, to go from 8 to 9 is a 10-fold increase. 9 to 10 is another 10. 10 to 11 is another 10. 10 to 12, or 11 to 12 is another one. So we do 10 times 10 is 100, 1,000. So we have 10,000 more of these hydroxide ions at a pH of 12 than we do at a pH of 8. And you know what's going to happen. They're going to want to give away that electron, or they're going to want to combine with other compounds and cause a lot of chemical reaction to the cell. It can be very dangerous to the cell. Okay, so we'll skip through some of this because we said all this stuff. Okay, here's just some ideas of some acids that we know about. Lemon juice, pH of 2.5. Stomach acid, like I said, is between 1 and 2. Even something like milk is actually slightly acidic. It's just a little below 7. You guys told me in your carbon cycle essays about acid rain just a little bit. We could talk about that a little bit, but those are all acids of varying concentrations and varying strengths. On the other end, from going 7 up to 14, we see that there are things that are basic. Okay, our blood is slightly basic. We're going to talk about why that is, and so is ocean water. We see up here bleach is a pretty strong base, and so is things like oven cleaner and drain cleaners and things like that. And you all know why. They produce these OH minus ions, which can cause damage to cells. Okay, this is everything I've been saying to you. Okay, I've been saying this a lot. This is basically why do strong acids and strong bases cause damage, but weak acids and weak bases don't seem to so much. So take a minute and jot down that statement that I just circled there to give yourself an idea of why that is. And what I wrote here is those H plus ions formed in acids and the OH minus ions, those hydroxide ions formed by bases, can cause certain chemical reactions that may interfere with a cell's normal functioning and can lead to the cell dying. And then down here, this is just an example of a strong acid in our body. Our stomachs have hydrochloric acid. Our stomachs have a layer of mucus on the inside of them so that acid doesn't touch our actual stomach. And in our stomach, we have an enzyme, because we're learning about enzymes here, called pepsin. Pepsin only works at a pH of 1 to 2. If you take the enzyme pepsin and you put it into water, which has a pH of 7, it'll denature. Remember, denature means it'll unravel, it'll lose its shape, and it won't work anymore. So certain enzymes in our bodies are designed to work at certain pH levels, and if you remove those from those pH levels, they won't work anymore. Okay, last idea I need you to know about is an idea called buffers. Buffers are weak acids or weak bases. So weak acid would be just a little bit below 7, so probably between 6.5 to 7, and weak bases would be between 7 to 8. They're found in ecosystems, they're found in our bodies, and what they do is they prevent sharp swings in pH. Remember, we have this thing called homeostasis, where we have to keep our internal conditions consistent and the same, even though outside might be changing dramatically. You all know that your body can't tolerate large swings in temperature or chemical levels or things like that. If that happens, you're ill. You're typically going to the doctor and they're testing you to see what's going on. So there's buffers built into our body so that we don't experience swings in pH. So say you drink a bunch of lemon juice, which we said had a pH of like 3 or whatever it is. Well, that doesn't mean that your body's going to go to a pH of 3. You would die from that. Your blood is actually a weak base. And if we eat some things that are acidic, and if that were to enter our bloodstream, this weak base that is a buffer called our blood prevents our blood's pH from dropping to like 3 or 4 or 5. Okay, it's just a little bit of a drop because this kind of balances it out because it acts as a buffer. The ocean is a buffer. You all talked to me about this with how the ocean can absorb a lot of CO2. And we said it's making the acidity of the ocean go up, but it's not going up dramatically. Okay, because the ocean water is kind of just like our blood. It's got a pH that's slightly basic. So it can absorb a lot of what we would call carbonic acid, which is what the CO2 makes, without its own pH changing all that dramatically and without, killing everything that's in the ocean. All right, so that's what you need to know about pH and about buffers. This is found in your textbook, and please let me know if you have any questions.